ClickHouse can query billions of records in milliseconds, but the challenge is bringing those billions of rows in there reliably. So while benchmarks highlight query performance, where production systems struggle is on ingestion. So let's understand why that happens. This is the ClickHouse ingestion mental model you have to take into account. We have seen this in other videos. Remember, you have parts, which are physical chunks created by inserts when you use the merge tree family. Then you have merges. These are background jobs that compact small parts into larger ones. And you have some kind of a budget because merges consume CPU, disk, memory, network bandwidth if you're using cloud storage. So you have to take that into account, okay? The model is simple. Whenever you insert some rows, it creates a number of parts depending on your partition key. There's this background process that compacts them in fewer parts. Okay, so remember, ClickHouse is designed for bulk inserts, not so much row by row streaming. And if you make parts faster than ClickHouse can merge them, what's gonna happen is you're gonna have a merge backlog, you're gonna have lag on your merge parts, and ultimately your queries are going to slow down because they need to read more parts that are not optimized. How many parts ClickHouse creates on each insert? Well, it depends on the number of rows you are inserting on each insert, the partitioning of your table. Remember that ClickHouse automatically creates one part for each partition. And then we haven't talked about materialized views, but materialized views are insert triggers, which means whenever you do an insert on a table, if there is downstream materialized views, it's gonna create parts for each materialized view, okay? And ingestion is not just about inserts. I mean, there is a fine balance between other things. Remember, we have merges, which have a kind of a budget because they use CPU, memory, disk, and network bandwidth. You have reads because they might be competing for resources. You have mutations, we already talked about them. Certain operations have to rewrite complete partitions. And of course, it depends on how you design your table. That's why it's important to understand how the engines work and how the partition key is important. Let's see some of the core bottlenecks when ingesting data in ClickHouse and why they happen. So first thing is throughput versus latency. Usually you want to achieve that sweet spot in which you have high throughput at the lowest latency possible, but there are several problems in here. If you make a bunch of tiny inserts, what's going to happen is ClickHouse is going to create too many parts. Actually, there is an exception, that's too many parts. And it's very likely that you're going to kill the cluster. On the other hand, if you do big inserts, if you batch insert, what's going to happen is you can risk latency. You're going to take more time to process those inserts, and you're going to need more memory for that. In production systems, what you usually do is you enable async inserts, so ClickHouse is going to automatically buffer the rows, and then you have a couple of system tables, system parts, and system merge, and you can monitor them together with your CPU, memory, and I/O, which is your merge budget, and you do some simple throughput math in which you calculate the number of parts you can create per second and adjust this insert block size. We've seen how merge read many small parts and write larger parts, and they consume CPU, disk, I/O, memory, etc. What you have in ClickHouse is a couple of settings to control how much threads you assign for that background merge pool, okay? Also for mutations. What you have to do in these cases is assign a value as high to not create a backlog of merges, to not create lag on how parts are being merged together. Also, do not produce a replication queue. Remember, different replicas have to coordinate themselves. So whenever a new part is created, there is a replication queue in Zookeeper, so the other replicas know there is a new part they can use for reads. So yeah, It's a fine balance in which, again, you have to try to not produce replication and merge queues, and you have some knobs, some settings, very low level settings you can tweak depending on your workload. Depending on your ClickHouse cluster layout, writes and reads can share the same system resources, CPU, disk, and memory. The balance, it's a little bit hard to achieve because if merges fall behind, what's going to happen is you're going to increase your ingestion latency, you're going to have a merge backlog, replication queue is going to grow. This is a huge problem. If you are very CPU intensive in merges, then your queries are not going to have resources to run. So it's very hard to pause one or tune one without affecting the other one when you have shared resources. And you may think, okay, I can go with separate replicas for writing, other for reading, so there is no shared CPU resources. I can do zero-copy replication, so we don't have the disk problem. Parts don't need to travel from one replica to the other. But even in that cases, coordination never disappears. So each replica is going to have its replication queue, and even when you have zero-copy, replicas need to know about the different parts that are available for reads. One important part is zero-copy replication is not available in the open source ClickHouse version anymore. And if you're thinking on adding separate writing replicas or multiple writers, this is going to complicate cluster management at different levels. When ingestion slows down, ClickHouse signals backpressure. There is a couple of settings to delay or error inserts when the number of parts is growing, but you're going to have a couple of problems in here. First, you need a way to rate limit your clients, and you need to make sure they retry again because you are failing those inserts. And when you need your clients to retry, you're going to have the deduplication problem. This is hard to implement correctly under load, and you can end up like duplicating several millions of rows, depending on your workload. The worst part could be even losing completely your data. Now ClickHouse benchmark is going to tell you this, which is systems are not immutable. You're going to need to evolve your schemas. When you do it, you're going to need to do data migrations, backfilling historical data. So the question is, can you keep your system running while you do these schema changes? There are several challenges on this. First thing is the primitives ClickHouse provides for schema changes usually trigger mutations, and we already saw how mutations need to rewrite complete parts. So this is going to compete with your merge budget, with your resources. Something important, and then you learn once you are in production, is in real clusters, you have ingestion and live queries. Then you do some change in your schema, and you have to simultaneously completely backfill the history to adapt to the new schema. So you have different moving pieces at the same time you have to manage correctly. And talking about backfilling, we will have a separate video completely about this. The most simple version of a backfill is doing like insert into select from your previous table. And again, this is a costly operation. This is going to spike on memory, on I/O, CPU. In the end, you are dealing with a complex system. You're trying to do ingestion yourself in ClickHouse, and there are different knobs, settings, metrics, and system tables you need to watch. It's very important that you measure how many active parts per partition, if the merge queue is growing, how many memory and disk throughput, if there are mutations, different zookeeper queues, DTL, replication queues, if there is lag in the replication, any other latency in zookeeper. There are some other backpressure indicators, if there is an increase in the insert latencies, even if there is an increase on your P95, P99 select latencies, then that's an indicator that something is wrong. And ClickHouse clusters are not static. They need to adapt to the load. So you're gonna do some of these operations, adding and removing replicas, dropping tables. You may have long-running queries when turning off replicas, and maybe you cannot do that. You may have S3 errors you have to monitor. So there is complex set of operations you have to do that you need to take into account what's going on the cluster at that time. As you have seen, ingestion in ClickHouse is not a trivial problem. There is a bunch of knobs that exist in ClickHouse because it was built for big infrequent inserts, not streaming ones. So it comes the ingestion proxy pattern, which basically is a piece of infra, a managed piece of infra that takes care of doing inserts through a buffer, so ingestion can scale accordingly. That speaks ClickHouse. We've seen how ClickHouse writes in parts, then merge them. They have to be optimized in size, in frequency for a nice balance of throughput and latency. And with all the built-ins installed, backpressure mechanisms, failover and retries, avoid the duplication, proper routing because you usually have many different tables with many different requirements, and a nice layer of observability. So let me tell you how Tinybird solves ClickHouse ingestion. This is a quote from a user this week who said, essentially, I want an endpoint where I can ingest all the data. So this is what developers have in mind. They don't have in mind like the tens of settings you need to tweak in ClickHouse, the number of things we've seen you have to take into account. Basically what they want is an endpoint where I can ingest all the data. And this is what Tinybird just provides. So first thing you have to do, we are in ClickHouse, you need to provide your table schema, columns, data types, JSON paths, because in this case we are ingesting JSON, and your engine settings. What type of engine, the partition key, the sorting key. These are the basics. We've seen this in the previous videos. You need to learn about this when working with ClickHouse. Optionally, you can define a token which is going to have append permissions over this table. Now, you want to insert data, you have an HTTP API endpoint, events API, you provide the name of your table, you provide the token with append permissions, and you send the payload. It can be one object, it can be several objects, okay? And Tinybird handles automatically all the ingestion problems we've seen you may have in ClickHouse. It's gonna automatically batch inserts, it's gonna provide backpressure management, it's gonna take into account schema evolution. Remember, you have live data, you change the schema, you have some mutations, some backfilling that's built into the system. It automatically coordinates replica, optimize merges, it provides logic for retrying and avoids the duplication. So let's go deep on how this works. Let me show you how Tinybird handles ingestion to ClickHouse. So this is your system, and your expectation is to send payloads to an events API. So every circle represents a payload. It might have different sizes, different number of rows, different size in megabytes, and every color means a payload for a different table. So now data gets to the events API. This is an HTTP interface that Tinybird provides that simply gathers events from your system. And those events are going to be processed by the gatherer. The gatherer is a buffer, an orchestrator between your producers and your ClickHouse cluster. Okay, this is your ClickHouse cluster. This is your system, and in the middle we have the events API and the gatherer. So what does the gatherer does? First, it provides a worker for each table that's gonna batch all the events into optimized parts. So it does not matter your throughput here because it's gonna automatically create per partition ingestion. So less CPU is going to be used in your ClickHouse cluster, and you're not going to have the too many parts problem. Now, it comes with automatic backpressure mechanism because it's constantly monitoring CPU and memory of the ClickHouse cluster. So whenever there is some server overloaded, it's gonna automatically delay flashes or enable some circuit breaker for several seconds or a minute depending on the CPU load. On the other hand, it also monitors memory because when you insert into a table in ClickHouse, you may have downstream materialized views, or you might have another process running on the same server, let's say a mutation, a backfill operation, and it can do several things. It can unlink an offending materialized view that's not optimized. It can increase the number of threads to process the inserts, or again, it can delay the flush to the system. It automatically implements routing. So for instance, you may have separate tables writing into different ClickHouse replicas. This is automatic. And it also implements failover mechanisms. So let's say you are ingesting this orange table into this replica and suddenly this replica goes down. What's going to happen is it automatically going to route to a different replica, and it's going to automatically retry the parts it has in the buffer with a deduplication window. Last resort, if the cluster is completely unhealthy, there is a dead letter queue, which is basically going to write all the parts to S3 so they can be eventually replied. So you're not going to lose data. It's going to handle retries with the duplication. It's going to batch inserts, and it's going to implement backpressure mechanisms while monitoring your cluster health, plus adding proper routing for to the most healthy replicas. Let's see how this works in practice. I'm going to open Tinybird code, and we're going to create a new workspace for a fleet management system. And I'm going to ask Tinybird code to create a data source for a fleet management system. So this is going to create a table with schema, with our columns, a timestamp, a vehicle ID, driver ID, a position, speed, etc., etc. It's going to be a merge tree, partition by month, and order by vehicle and timestamp. That's good. Now I'm going to deploy the schema to the cloud. And if we take a look at the data source that we just created, we have a fleet events here, and we have a button to ingest data. I'm gonna click it, and this is how you use the events API for this specific data source. So from the point of view of a developer, I just have to worry about creating the schema, defining the proper engine, partition and sorting key, and then start sending events from my system. So let's see an example. I'm going to copy this, and if I run it from the terminal, we're gonna see we've ingested one row. We can do this as many times as we want, and we can even try to send thousands of events per second. Let's try to do it. So we can save, for instance, the payload in a JSON file, and we can use Apache events to send 10,000 requests in batches of 1,000 records. And I don't have to worry about anything else. I just have to send my events to the API. And as we have seen, the gatherer is going to batch the right parts. It's going to buffer them. It's going to flash them to the proper ClickHouse replica, and I don't have to care about any of the settings that manage ingestion in ClickHouse. And if I run an SQL over the fleet events table, we see we have there our data. In this video, we've seen the hard parts of ingesting into ClickHouse, especially at scale, and how Tinybird provides an HTTP API and an ingestion proxy and orchestrator, so you don't have to worry about the internals of ClickHouse and just worry about sending events and build your analytics products.